My project is about comparing these 5 sorting algorithms, but why is sorting important?
Hi, my name is Aditya, and I'm a student at the North Attleboro Middle School, and I'm doing a programming project on the efficiency of sorting algorithms, and that's why I'm here at the Richards Memorial Library that houses more than 45,000 books.
So, say you were trying to find a book in the library called iFunny by James Patterson. Well, libraries are usually organized in 3 categories: children's, young adults, and adults. And then inside of those, they're organized into fiction and nonfiction, and then they're organized by the author's last name. So, if we're trying to find this book, first we'd find the children's section, which is where I am. Then you'd find the P for Patterson, and then you would search through that until you find the book. So, imagine if you had to find this book in a library that was not sorted. It would take forever. And we might be onto something here. Really fast search engines like Google employ the same technique. They sort their data before they search. This is why they can find millions of results for any search in under a second.
So, how do sorting algorithms actually work? Well, bubble sort, one of the simplest sorting algorithms, works like this. So, you compare adjacent numbers. 3 is not bigger than 9, 9 is not bigger than 10, 10 is bigger than 7, and 10 is bigger than 6. This first pass means that the largest number has bubbled up to the right. 3 is not bigger than 9, 9 is bigger than 7, and it is bigger than 6. Now, in the second pass, the top 2 largest numbers have bubbled up. And you keep repeating this until you have a completely sorted list. This is quicksort, and it's the fastest of all sorting algorithms. I wrote this flowchart to explain my code. At first, it finds if the list size is greater than 1. If it is, it makes the middle number the pivot. Then, for each of the numbers in the list, it compares it to the pivot. If they're smaller, then it moves it to the left list, and if they're bigger, it moves it to the right list. Once each of the numbers have been either moved to the left list or the right list, it sorts either of these lists recursively using the same code. At the end, you have a bunch of lists with only one number in it, all sorted in order, and you combine them to make the final sorted list.
This is my code. I wrote it in a language called Python, and I wrote it in an editor called PyCharm. As you can see, all of my programs are on the left-hand side: bubble sort, comb sort, insertion sort, quick sort, and selection sort. I wrote all of this code myself, and I did not copy it nor download it. But I did learn the algorithm theory from other sources. So, this is bubble sort with a little more depth. If a list consists of 5 numbers, for the first pass you have to do 4 comparisons, for the second pass 3 comparisons, and so on, and you'll have to do 4 passes. So, generalizing, for an array of the size n, there will be n minus 1 comparisons of numbers and n minus 1 passes, which is about n squared operations. So, this is all of the different sorting methods in different data sizes and the time it took them. So, for bubble sort and selection sort, it took bubble sort about 1 hour and 30 minutes, insertion sort about 1 hour, and selection sort about 30 minutes. It took a long time just for 300k numbers, whereas comb sort and quick sort took a very short amount of time, about a second or 2. And this is mainly because of the number of comparisons these different algorithms have to do. And I compared it to n squared divided by 2. And so bubble sort and selection sort took several 100,000 comparisons of numbers for 300k. Insertion sort took around half of this, and comb sort and quick sort took a very, very small amount, to the point where you need to look for it in the graph. And so if you put this on a line graph, you can see that bubble sort, selection sort, and insertion sort, the number of operations and the time increases exponentially as the data set increases, and that comb sort and quick sort barely even changes. And so this shows that quicksort is the fastest, comb sort is the second fastest, and selection sort is the third fastest. Thanks for listening.